let's see. Looks like we got a string going here. And, yeah. What's up? I'm looking for my audio to be coming through and stuff. And of course, I've got somebody who's coming to interrupt me, like right when I get going. Um, but yeah, so I've got 15 minutes before I've got an email out to some people that might come in. So I was gonna just come on here and start doing some calculus, and we're gonna start just going through this stuff. I'm rusty as all get out. I haven't done this particular stuff in quite a long time, but gotta start somewhere to get back into it. So this is at Gonzales Hill. This is what I did my undergrad with, or whatever. Chapter 12, Cartesian space coordinates. All right, so think of it like when you have graph paper, um, except 3D. So you've got an x-axis and you got a y-axis, and you can be in positive x or positive y, and that's going to be the first quadrant, etc. But if you extended another axis up out of the page, right, that would be the z-axis, and then it would be three-dimensional. So yeah, for our purposes, we're going to start considering the 3D space or whatever. So what does this say? To introduce a Cartesian coordinate system in three-dimensional space, we begin with a plane Cartesian coordinate system, which is what I just said. O-XY, it's an interesting notation. So you just got, that's your graph paper or whatever. Through the point O, which we continue to call origin, we pass a third line perpendicular to the other two. You get that? Perpendicular to the other two. That means if you look at the angle between this new axis that we're adding, the z-axis is going straight up, and relative to the x-axis we have a 90-degree angle, and also relative to the y-axis we have a 90-degree angle. So we say it's orthogonal to the plane or perpendicular. All right, so what else does this say? This third line we're going to call the z-axis. We assign a real number coordinates to the z-axis in the usual way, right? So when you started algebra and they said, well, you've got the real line, that's going to be your first axis or whatever, and it's really the set of real numbers. It's an infinite, uncountably infinite set of numbers that contains simpler sets of numbers. At the very outer boundary where you have the real numbers, you're going to have numbers that you can only get by calculating, doing some calculation procedure to get more and more accurate to it. But the number pattern, like for example the Euler constant, you're going to calculate 1 plus 1 over n to the n power. And for a large value of n, you're going to get a longer and longer number, but it's 2.71828, and it goes on, a non-repeating pattern. So the real line contains all those kind of numbers like that, transcendentals that you can only get through some kind of iterative procedure, and irrational numbers like the square root of 2, numbers that are you can use methods of exhaustion, like to get closer and closer to calculating the square root of 2, but it's a non-repeating decimal. The simpler sets that are contained in the real line are the counting numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And they're additive inverses. That's going to be called the integers. So you have the natural numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you know, it just goes on forever. And you have, if you add to that set the additive inverses, right, of that, you're going to have the 0, 1, negative 1, 2, negative 2, 3, negative 3, right, on to infinity, right? And then you've got numbers that can be represented as a quotient of integers, right? So that includes really, you, you know, 2 can be represented as a quotient of 2 over 1. It really is. It is divided by that, right? And then you're going to have 1/3, 2/3, 17 fifteenths, all the rational numbers. And their additive inverses or whatever. So you start with the x-axis, you've got that whole infinite set there, uncountably infinite. And then you add another axis, the y-axis is also the reals. And then you add the z-axis. And what ultimately you end up with is, I like to, we call it R3. If I, hold on a second. We'll say, right, like that. Beautiful. I love that. Okay, so that's where we are. Okay, so I'm going to go ahead, turn this bad boy back on. All right, so z coordinate, obviously, for 0 is going to be the same place as x and y. It's the origin. So the origin vector is just the vector, the order 0, 0, 0, 0. All right, so for later convenience, we orient the z-axis so that O, X, Y, Z forms a right-handed system. All right, this is tricky. That is, if the index finger of the right hand points along the positive x-axis and the middle finger points along the positive y-axis, the thumb will point along the positive z-axis. All right, so let's look at this drawing carefully. All right. So there's your right hand, and you're looking at positive z. And the index finger is positive x, and the middle finger is pointing to positive y. So think of it like that. All right. The planes determined by the x and y axes, and the x and z axes, and the y and z axes are called the coordinate planes and are labeled the xy plane, the xz plane, and the yz plane. So, yeah, all of a sudden I can go from looking down flat at the paper and seeing the xy plane, right, to like looking sideways. Here's the positive y-axis and the z-axis. So I've got the the yz plane going this way, right? Or the xz plane. Here's x coming across like this, and z, so it's coming up in front of my face like that. All right. Now, whenever you go into a game development program, really, when you go in to make your game in Roblox, or you go in to make your game in Unreal Engine, or you go in to make your game in Unity or something. Hold on a second. I'm also in a Google Meet, so if you whenever you go into any of those game development applications, you're going to see like an X. Typically, you'll see like an XY plane stretching off into the distance, some kind of a grid or something like that. And then it's a given that Z is going up, right? Another way that it can be oriented in some applications, I think, for example, in Maya, when you're looking into space in Maya, you're seeing the XY plane, and the Z plane is coming out towards you, the positive Z plane, right? That's another way that you can think of it, right? But you should play around with that stuff in your mind. So here we have a claim here, a statement. If P is an arbitrary point in space, if, then, right? If P is an arbitrary point in space, then the plane through P, parallel to the YZ plane. All right, think about that. So here's a point, and just for the sake of argument, let's say it's not coincident with the YZ plane, but I've got the XY plane here, and then positive Y is going this way. So here's this Z plane, and here's a point P, and it says parallel, right? The plane through P, parallel to the YZ plane, will intersect the x-axis at a point x naught. The plane through, you see how that works? It's going to drop down x naught, right? We're going to have a nice little drawing of it here too. Here, just a second. I'm gonna, the plane parallel to the XZ plane. Okay, so here's the XY plane is going like this, right? So here's the x-axis. Right? So the XZ plane is going to go up like this, right? It's going to intersect the y-axis at the point y naught, right? So say it's offset from the actual. It's not coincident with the XZ plane. So, but it's going to hit that y-axis. It's going to go down. It's going to hit that y-axis somewhere, and that's going to be y naught. And the plane P parallel to the XY plane will intersect the z-axis at a point z naught. We associate P with the ordered triple of numbers x naught, y naught, and z naught, the Cartesian or rectangular space coordinates of P. Get that? So here's another way of looking at it. If I'm on the x-axis, I can move in the x direction until I line up with P, right? At some distance x naught. And then I'm going to move in the y direction until I line up with P along that axis. That's going to be y naught. And then I'm going to move, so I move x, y, and then I'm going to go up until I line up with z, excuse me. So the coordinates of P are going to be x naught, y naught, z naught, whatever those positions have to be. The Cartesian or rectangular space coordinates of P are simply the space coordinates of P. In particular, the point on the x-axis with x-coordinate x naught has space coordinates 0, y naught, 0. Because why not? And the point on the z-axis with z-coordinate z naught has space coordinates 0, 0, z naught. Alright, so let's take a look at this, right? So I could have a plane through this, and a plane through this, and then a plane through this. So if it was shaded, you know, let's see, a plane defined by these two, right? And I would also see a plane defined by these two here. All right. A point is in the xy plane if and only if it is of the form x, y, 0. Thus, an equation for the xy plane is z equals 0. That's a very simple equation for the xy plane. All right. So z equals z naught is just a plane that doesn't intersect the xy plane. Right? So it's perpendicular everywhere. And it's elevated or it descends to whatever z naught happens to be, negative 17, positive square root of 2, or whatever it is. All right. It represents a plane parallel to the xy plane, z naught units above the xy plane, when z naught is positive. Absolute value of z naught units below the xy plane when z naught is negative. Similarly, equations of the form x equals x naught constant represent planes parallel to the yz plane, and equations of the form y equals y naught. Because why not? Constant represent planes parallel to the xz plane. See, for example, 12:1,3, where we've drawn the planes x equals 1 and y equals 3. So here's, I like this better. It's like a shaded version of it. Now these planes, of course, extend forever to infinity, right, in every direction. Excuse me. But I like the drawing when they also have the z naught or whatever plane, and they draw that into and shade it, and we'll probably get that a little bit later on. Let's see how we're going here. This stuff, it's not that bad. Right? Don't flip out. Right? Let's see if I can do this. The distance d from P1 and P2 in the space, right? Now, you're seeing all this gobbledygook here, and I just want to. Oh, wait a second. Somebody's saying something to me. Hey, Trantastic, is that you? Hold on. I don't know. Did the chat box just come up? Really, you can get these distance formulas, right, from the Pythagorean theorem. Let me see if my buddy's on here. Let me get the chat box up on the top. Yeah, it looks like he's just come on here, but I don't know if you're still on there. You want to call on Discord and follow along and learn how to do calculus? Fantastic. This is my buddy. Yeah. Let me just go ahead. Let's see what I've got to do here. Figure out where's the best place to put this guy to monitor what's going on here. And what I need to do is go to the chat box and refresh cache of current page. Close that out. Okay, that's going to clear that out nicely. And I'll bring in on this call. I'm gonna hold on. Let's see. Traintastic. What do you have here? You're like, okay, distance d p1 p2. What the hell is that? What's that even mean? Well, think of it like, say you've got, let me think of a good way to put this. Say you got a ping pong table, and there's a ping pong ball sitting on the table, and there's a light fixture overhead, and there's the light bulb. Now the center of the light bulb is a point P1, and then the center of the ping pong ball is a point P2. And you're wondering, is there a way I can calculate, the distance between those objects? Which is what your game development software does. Hold on a second. You know what? He may be talking, and I may not be hearing because I'm... Hey, can you say something? Shane Tustic, are you there? Started a call. I don't know if he's talking or not. I can't... Oh, yeah, okay, so I can hear you. So, let me ask you a question. Let me ask you this. Can you recite to me the Pythagorean Pythagoreanizationalism of theory? Do you know what the Pythagorean theorem says? Okay, all right. So well, I'm doing this thing now. I'm actually working on starting a math sort of club, right? And I've got what I did last night is I had about 9 people that had written and expressed interest in the club, and I was like sending them messages one by one, and they were sending me messages one by one. So last night what I did is I set up a Google Meet. And I put them all, so they're authorized to join this meetup on Google. But I'm also streaming it. Now, if you just want to, let me hold on a second. So how you been doing, buddy? I'm gonna close this down. Right. So we're in R3, and what is it? What? Yeah. Okay. Yeah. I wonder about that. Is that so here's a line. It's like 5 units long, and here's another line that is 4. And really, like if I'm in Roblox and I'm building a game or whatever, I can see there's an origin, and yeah, I wonder why it's so slow and jittery and stuff. But it shouldn't be. I got a damn I've got an RTX card on here, right? Yeah, but the camera's a dang. It's expensive. Got $80 document camera. It should be like really fluid. I'm not sure, but anyway. Yeah, I don't. It's like there's a light on this thing, but I can't stand the light. It's too bright. But I can basically draw a line right here, right, and I can notice something about uh, this line. Like, let me see. If I make a square, I've got what? How many squares is that? 16 little squares, right? Alright, so I can make another square down here. It's going to be 5 across and 5 across. So these are 16 squares, and this is 25 squares. Uh, fourth, is that right? No, is that what I want? 3, 4, 5. I should, no, I'm doing this wrong. I should do 3, 4, and then have 5. So I shouldn't have done this way. Let's do it again. All right. Let's go 4 and 3. Now when I make a square like this, and I make a square like this, I've got 16 and 9. Now what's 16 plus 9? Dun dun dun, it's 25. Right, so. Right, that means that this area, we're going to say uh, um, 16 and 9. If you add it up, it's going to be 25, right? So this is what's called, this means that for any right triangle, the simplest way to put it, that if I take this side and call it A, and this side and call it B, then there's an equivalency with this side C. And we say A squared plus B squared equals C squared. And this goes back, I mean, the Babylonians knew this, right? There are various ways you can draw it, or you can lay out, like if you make a bunch of little cubes and line them up like this, you can see that it always works. This A squared plus B squared equals C squared. This is laying out like squares like this is kind of a geometric way of proving it. There's different ways to prove it. But what we're concerned about is if you're doing something on the computer, like you got a spaceship and it's moving in space or whatever like that, you can't just have something to know a point like where it is. Like if you're playing an arcade game, you know how it's kind of 2D? Like you're playing an old game like Defender or something, or Joust or some ancient arcade game, or Space Invaders, right? It's just X and Y coordinates, right? But a 3D game, we need mathematics to move things around in 3D space. Now this A squared plus B squared equals C squared is one way, but if we added another axis, right, we get the three-dimensional coordinates. So let's see, A squared plus B squared plus C squared is equal to D squared. And that's going to put us into three-dimensional space. Now I'm going to see, say for example, I start out in the plane. So here's my origin. And I'm gonna go some direction. Well, really, what am I concerned about? It's like I need to know, say for example, the length of this line. How long is it, and where is it, right? So I make a coordinate, right? And it's like going along the x-axis. Here's the first x value, and I'm just going to call it x sub 0. Right? And that's the one that's going to line up with this, right? And I keep going along, just want to keep it general. I can see that this is actually 1 on my graph paper, right? But I'm just keeping it random so I can derive a general formula, right? So I go along, I keep going along, and then I've got x sub 1. So x0 and x sub 1. All right. Now, how long is that? Well, I can see it. You know, since this is 1 and this is 3, 1, 2, 1, or this is 4, right? Can't you see? You can see that's just 3, right? The length of that is 3, right? But if I'm just calling it a variable, I can say, well, this distance here, whatever that, it could be, you know, the distance from the center of the sun or something. It could be anything, right? I could say, well, then this distance here is going to be x1 minus x naught. But here's my first side of my triangle, which I call A. Right? Now let's look at the second side of the triangle. I'm going to call B. Right? Well, along this axis, as I go along the y-axis, oh, lo and behold, there it pops out again, right? And here is my first y, which is y sub 0, and I keep going along again until I get to y sub 1, right? And I can see again that this distance here, b, is going to be whatever y1 minus y naught is. For example, if I'm going by the graph paper, this y naught would be 1, and this would be 4. 1, 2, 3, 4. And 4 minus 1 is 3, and 3 is how far it is from here to here, right? Okay, so I now have the second distance, y1 minus y naught. But the Pythagorean theorem tells me a squared plus b squared is equal to c squared. I don't want to get too far off there. Right? So what I can do is I can say, take this squared plus this squared, and that's going to be equal to c squared, which is, that's the length of this line squared.
I want to play outside with both of you because I want to have fun.
My daughter's getting an argument with her mom. So I want to be playing outside with both of you because I want to have fun. Yeah. I don't know what she's doing, but I may need to go check in a minute. What is it, dear?
I wanted to go outside with you and the mama.
Okay, well, let me see. Okay, I'm 20 minutes into this thing, so I may need to get off and take my daughter outside to play. But I wanna finish this one thing to see the point of this all is that I've got the length of this line, right? And well, I've got the square of it by the Pythagorean theorem. So what I can do is take the square root. So this c, I just take the square root of c squared is equal to c, which is going to be equal to, take the square root of both sides, and I've got the square root. Okay, you're going to have to wait just a minute here till I get done. Of x1 minus x naught squared plus y1 minus y naught squared. And now what I've done is I've derived, hold on just a minute, dear. Don't interrupt when Daddy's teaching a class, right? You can't interrupt the teacher, right?
I'm going without you because you're not listening to me.
She says, I'm going without you because you're not listening to me. I am listening to you, dear, but it's very rude to interrupt a class. You got to learn not to do that, right? I'm not going to get mad at her or anything like that, but I got to make it clear that, yeah. So, this is a derivation, right, of what's called the distance formula, right? So we can extend this this principle into the Z plane, which is what I'll try to do next time. Okay, that worked out pretty good. Okay, and I was on till 4:20, which is, yeah, I've scheduled like a Google Meet, and I invited these people to come in. Um, but it may not be a good time. I haven't heard back from them yet. It's like all these people are writing me on Craigslist. Yeah, I want to do a math club. I want to get together online and do math or whatever. Or actually meet up in some of the libraries or something around here. But we're just getting started, so we're going to see how it goes. So everything going okay with you? Groovy, man. That's cool. No, but I need to go and take my daughter outside and play. All right, man. Take it easy. Thanks. Yeah, thanks for calling. Good to see you. All right, bye. All right, bye. And I'm signing off. All right.